Well, thanks all for staying till the very end. I know what Neil's talking about with that light. That's quite nasty. So, yes, I have a confession to make. When John asked me to give this talk on managing Sodic soil nutrition, I thought, yep, no trouble at all. I got heaps of information on that, and there's got to be something in there about cereals. As it turns out, I haven't got anything at all on wheat or barley or chickpea or anything. But how many of you actually manage cotton? Oh, that's good. You've stayed till the bitter end and you've got cotton at the GRDC update, which is fantastic. A few take-home messages. So I will not go through the hard science that Neil has just covered. I'm going to talk more about our experience working with cotton and the practicalities. We're trying to tease out. Neil raised that problem at the end. He talked about how we're got to work out how there are these multiple effects of sodicity on plant growth. And so we're trying to, a few years back, tease out the importance of those effects. How important are the chemical constraints versus those physical constraints in verticil soils? And it was the cotton industry that first funded us to have a look at that and has continued to fund subsequent postdocs. So I'll be building on the work of Kylie Dodd, Dr. Dodd now, and Dr. Rebecca Haling, who have been funded by cotton to look at sodic soils and sodic phosphorus nutrition. So I'll talk about phosphorus at the end, and I did panic about the fact that I had absolutely no wheat or barley or anything remotely resembling grain in my talk, so I did an experiment to dazzle you with at the end, and you'll see what happens when you do things quickly as scientists. So what are the take-home messages? As far as we can tell, most of the early low sodic, moderate to low sodicity effects are associated with the soil physics. So managing and improving soil physics is a good way forward to dealing with sodic soil nutrition. I was trained by Neil. I was, I think, his first PhD student at UQ, and I would love to stand up here and talk more soil chemistry because I was trained by a soil chemist, but unfortunately it turned out that much of the problem was soil physical, and I find soil physics less interesting, shall I say, than soil chemistry. But it was soil physics that was driving down yield. And the specific aspect of sodic soil nutrition, I think, at this stage of the research process is to do with waterlogging. That managing that root zone and managing and reducing waterlogging is a key aspect. The final message would be, where should we be directing funding? Neil highlighted it as well. It's hard to manage subsoil sodicity. How do we get the activity of calcium in that soil solution high enough to not limit root growth? And so trying to work out strategies to make available the water and the nutrients at depth would be a really good way to move forward. So here's a picture of a field near Moree, Moreton Plains. I don't know if you're familiar with that one. Kylie did her PhD out here and took the soil from there. That's just an EM map. The circled areas are areas of high sodicity. Now, I'm not saying that you can map sodicity with EM. I'm just saying that potentially there's a coincidence of salinity and sodicity in this field. But as it turned out, there is in fact a correlation between the sodicity and the salinity perhaps, although the salinity was not at a limiting level. This is not highly saline soil, but there was enough variation there in sodicity that we saw depressed yield. So what is causing the depressed yield in that field? So for cotton plants, this is typically what you see, and if I can work out the red light. So as our dry weight decreases, we see our sodium go up. So that's perfectly understandable. We've got increasing sodicity, and we're seeing increasing tissue sodium in the cotton leaves. And at the same time, we see potassium going down. So it seems really obvious that as we move into a sodic soil, we're seeing more sodium in the leaves and less potassium. The solution to that should be obvious. We should just add more K. And the reason Kylie even started her PhD was because she was managing a lot of sodic country, and she was seeing that the response of producers, which was to add more nutrients to the sodic low yielding parts of that paddock, was not resulting in improved yield in any way, shape or form. It had no effect. The potassium was not available to the plant, and it wasn't fixing the sodicity problem. And that's because of these multiple effects. It's not as simple as dumping more K in to overwhelm the sodium. As Neil mentioned in his talk, when he put up all of that plant physiology stuff and the whole liquid bit inside and all that type of stuff, I'm not going to go through that, but that is an energy intensive process. And just like when you ate your lunch and you are digesting it, you are respiring it, you are using energy. You are getting energy out of that food, and you need oxygen to process that food. If in this sodic field there is no oxygen, you have irrigated it, you have put the water on, and the root zone oxygen levels have fallen, the roots have stopped functioning effectively. How long do you think it takes for a root to pretty much start shutting down? I'm going to throw that out to the audience because it's getting really late in the update. How long would it take you to survive if I tipped you upside down in a bucket of water? A minute, that's pretty good. A minute. If you're a deep sea, one of those deep sea divers, we're talking maybe 12 minutes. How long do you reckon it takes before a root shuts down? I'm supposed to just give you the information, aren't I? I'm getting nothing back. I'm seeing a bright light. There's a bright light, but 30 seconds. Oh, golly, 30 seconds. That's, God, plants would drop dead just a shower of rain at 30 seconds, wouldn't they? No. So if you're going to shut it down, it's about a day. That's right. About 24 hours. Okay? So the question becomes, okay, we're going to flood irrigate this cotton. How long will it stay waterlogged? How long are we going to turn our root system off? Because what happens in that root is if you've got no oxygen, all those little channels that Neil was talking about, all those channels require oxygen and energy to work. If you've got no oxygen, they're not working. Not only do they not work, so they can't take that potassium up against that concentration gradient, they can't do that, but they actually just become flabby and slack and loose and lazy, and they let anything in. They'll let anything through that door if they are essentially starved of oxygen and mostly dead. So the reason the sodium's going up is not because the plant can't keep the sodium out because there's so much there. The plant can when it can breathe, but once it's drowned, it becomes leaky. And so the sodium's going up as a consequence of that water. Does that make sense? It's got nothing, it doesn't matter how much K we pour into that system. The plant can't take it up and discriminate and take it. It's just going to be leaky, and it's going to take up sodium, and then we're going to have problems. So it's a diagnostic feature. So we did some research trying to separate out those physical and chemical effects, and I'm considering waterlogging as a physical effect of sodicity. So we used PAM, and at Coonabarabran I was asked about PAM, polyacrylamide. You can buy it now. It was used and really big in the 50s and 60s until they worked out that it was toxic and it was going to kill things really badly, so it went all quiet for a while. But then they've worked out how to make ones that are no longer as toxic as the old ones were, and so it is possible to purchase. It's essentially functioning, because it's an organic compound, it's essentially functioning like out of a can organic matter, I would suspect. And when you try and mix this through a sodic soil, it becomes like snot. And that's what Kylie was doing with a great big stick, with a great big tub of soil. She was mixing snot. The beauty of the PAM is that it very, very effectively overcame all those physical problems. We no longer had physical constraints in that soil. And in fact, when we applied PAM to a completely non-sodic vertisol and grew cotton in it, and we're talking in like 60 kilos of soil, so not small volumes, the plant actually grew better because vertisols, as a general rule, are a hostile environment for roots. And if you make them physically better, the plant just goes, hey, and grows even better. You can ameliorate a non-sodic soil with PAM. I'm not going to stand, I don't sell, I have no shares in PAM companies. That's just the tool that we use to eliminate the physics without changing the chemistry. And what this graph is showing is that for ESPs up to about 20%, if you can fix the physics up, the cotton was perfectly fine. If it's free draining and there's no physical constraints, there's plenty of air, there's plenty of water being held, not an issue, up to about 20%. Once you go above 20%, some of those chemical effects kick in and we start to, that sodium does become a serious problem. But in the surface of most of our vertisols, we're looking in the top 30, we would be below 20 in many of them. And I know all of you would have properties that you manage that have 30 at the top and you just go, what do I do? So if we're going to use potassium as our indicator, when we add our PAM, we see as ESP goes up, we see no effect on tissue potassium. There's plenty there that is above the critical level for cotton. It's all good, the plants are happy, everything. We actually worked out what the solution chemistry was in that sodic soil, and we put it into a great big tub, 300 litres, and we grew cotton in that in sodic soil chemistry, and we saw no effect whatsoever. The plant didn't care as long as there was air bubbling through that water. The actual nutrients made no difference to the plant at all. You must be wondering, is this the same for wheat? Does it affect barley in the same way? And we haven't done those experiments, but the environment is still the same. If we can fix the physics, then I would suspect we're going to improve the nutrition. Oh, I didn't mean to press that one there. But as we increase sodicity, we decrease our potassium, as expected. So we investigated this waterlogging in a little bit more detail, and we used radioisotopes because we're at a university and someone gave me a license to use that stuff. I'm actually the chair of the Radiation Safety Committee at University of New England, and I think that's very sad for the University of New England that they think I'm responsible enough to play with radiation. But anyway, we used P32, and we decided we would use P32 to work out when the roots were going to recover. Because phosphorus uptake is also an energy-intensive process. You need the oxygen there. We're going to work out when did the roots turn themselves back on in these soils. So we had control pots that we didn't waterlog, and we injected with a long needle from a reasonable distance, because P32 is not the nicest thing on the planet, and I'd had all my kids by then, so it was all right. And we injected it down, and then we waited. If the roots are active, they're taking that phosphorus up, and we can get a Geiger counter and the leaves will start beeping at us. So we did that, and you can see there, we injected it down. It took a couple of days for the roots to actually find where we'd put it. They're busy growing, and they found that in 2 days. Even in the waterlog situation, in the non-sodic one, so ESP of 2, it's taken a little bit longer. So it's drained reasonably freely in that sodic situation. The key one though is look at the difference in moderate sodicity. It has taken more than twice as long for the roots to turn themselves back on after flooding in the sodic situation. The rate at which the oxygen could get back into that sodic soil was so slow. In the field, this would be exactly the same. When you flood irrigate a cotton field, I would hazard a guess that you are turning your root system off for up to 9 or 10 days. One reason potentially that all sorts of issues around how to manage our phosphorus and potassium and premature senescence and stuff like that in sodic situations, you are essentially turning the roots off for 10 days. And this is a physical problem. If you can overcome it, it's all good. If you look at the really high sodicity, even in the control non-waterlogged soil, chemically, the way the roots are extending, there could be calcium deficiency induced, etc. It took quite a long time in the really highly sodic soil. But at that moderate zone, we were seeing essentially low root activity. Now these experiments, they're hard to do. They're hard to do in the field. They're even harder to do in the glasshouse. Cotton has a really cool little feature in it that if you try and grow it in 3 or 4 kilos of soil, it very rapidly finds out that you're messing with it. It puts its root out and it hits the side of that pot and it says, hang on a minute, there's not much space over here. And it goes the other side and it goes, there's not much space on this side either. And so it decides it's going to go bonsai on you. And so it decides, I'm only going to grow this big because you've only going to give me this much soil. So the dynamics of doing this type of stuff in very small soil volumes means that scientists have trouble managing this, which is why we don't do our cotton experiments often anymore in less than 5 or 6 kilo of soil for more than 5 or 6 weeks, just because we don't want the plant to sense the side of the wall and send that feedback back to the shoots saying, I wouldn't get too big, guys, because we're going to die in here. So, but we did do some experiment with Dr. Beck Haling, and we were looking at sodicity effects on phosphorus nutrition. So that's really hard to see in this room. It was easier at Coonabarabran. But you can see here, this is the control treatment and this is the Sodic treatment. And this is 2 rates of phosphorus, 2 milligrams of P per kilogram and 20. The plus and minus refers to mycorrhiza. We have had all sorts of trouble with mycorrhiza, and so there was a question about soil biology. At the moment, we are yet to inoculate successfully mycorrhiza into a sodic situation. So part of that was probably the fact that just about every single package mix of mycorrhiza inoculum that you could buy off the shelf has no spores in it and doesn't work. But when we actually get some mycorrhizally inoculated roots and mix them through, we still struggle to get mycorrhizal infection in the sodicity. So I've got a PhD student chasing that down right now because that's a game changer in my head. If we're losing our fungal friend in sodic soils, maybe that's got a fair bit to do with our premature senescence, etc. So we're trying to chase that down now. We're hoping that we can get it to infect and get it to work. We're working at Yambacully just down the road here using their soil, but we've got no mycorrhizal infection. But what do you notice here? You notice these plants are all exactly the same. The control ones are slightly taller. There's no effect of phosphorus. There's no effect, and this is a P-responsive soil, no effect of sodicity. It's a dud experiment as far as we could tell. Why is that? It's because we were very careful with the way we watered these pots. We actually eliminated those physical constraints by the care with which we watered the pots. We watered them to just below field capacity so that there was always a bit of oxygen there. And when we do that, we lose what we're actually trying to test, which was a problem for us. What I'm saying is it's hard to do these experiments, as Neil was saying, carefully and actually draw the sensible conclusion. And so much so that in those small, well-managed pots, really crazy stuff can happen. So this is our non-sodic soil, and we're just looking at how much shoot we get, and we get, as expected in the non-sodic soil, no effect of gypsum. Everything's fine there. But we do get a response to phosphorus. We have increased growth in response to phosphorus. So everything works really well. But we go over to the sodic soil, and the story that we've been telling you is gypsum is going to cure everything, isn't it? What do you see on that slide? The sodic soil, we add gypsum with decreased yield in a very small, well-managed pot. What's the deal there? Why has that happened? One of the reasons we think that might have happened is because when you add gypsum, not only does the calcium precipitate out as calcium carbonate, but it probably also precipitates out calcium phosphate. And so we've lowered our phosphorus concentration solution. But when we measured the soil solution phosphorus concentration, I still didn't think it was low enough necessarily to have caused this effect. So we're again chasing that down, and I put a call out about 2 years ago when we were doing this for anyone with Sodic soil to just send me a 1 kilo bag, and we were going to just do a simple, okay, let's see if this really happens in the field in your soils. I'm just going to add some gypsum to your soil and see what happens to the phosphorus concentration. But we only got like 6 soils back, so I'm going to have to go and dig the holes myself, I suspect, and just randomly lob up on people's properties. Enough cotton. This is my attempt at introducing grains into the GRDC update. So 4 weeks ago, I thought, oh gee, all my data is on cotton. I have nothing on wheat. GRDC is funding me to look at root systems, which is really, really good fun. And we've developed a really cool technique to look at those root systems using CT scanning, and I think I've presented that at the updates in previous years, even last year. So we used our system. We're using pool noodles. Why pool noodles, do you think? It's not because we've run out of money and they haven't given us enough and we can't afford actual plastic pots. It's because a pool noodle is essentially air. And when you're firing X-rays through it, the pot vanishes, makes it really, really easy to see the soil and the roots out the other side. Whereas the density of an actual pot is a bit too close to the density of the root that likes to actually crawl down the side of the pot, as any of you have grown houseplants would know. So we're using pool noodles. Which one do you think is, I've used 3 treatments there. This was done in half an hour. I rang up my GRDC root team and I said, I'm giving a talk in 4 weeks. Can we just get some Sodic soil? We'll treat 2 lots with gypsum and 2 lots with PAM, and we'll not treat 2 lots, and we'll see what happens. And we'll scan these roots because we're really quick at it now. And we literally scanned it the day before the Coonabarabran update last week and pulled it together. Which one do you think is the gypsum treatment? This one? This one? 1, 2 or 3? You reckon this one over here is gypsum? It's not that that's actually a hose there, that's not actually a wheat plant. I'm just looking at that going, that might actually look like a wheat plant, but there's our wheat plant there. So this is our control over here. The really happily growing big one. Compared with our treatments, which is gypsum here, the small runty one that has almost died from us treating it with gypsum, and the PAM over here, which looks can be deceiving with the hose, is still pretty ordinary. And I've gone, bugger. That's what happens when you do it in half an hour, 4 weeks before a GRDC update. I'm expecting the exact opposite. But the shoot growth is fantastic here. This is Spitfire, and Sharon actually gave me the clue as to maybe what's happened is that GRDC has such a fantastic breeding program for the north that they might have bred plants that love Sodic soil. And the moment we fix it and make it actually a nice place to grow, they don't know what to do and they die. That's as good a theory as any, as far as I'm concerned. I'm going to keep playing with this. It's a mystery to me. What did the root systems look like? When we look at the scans, we had a lot more shoot growth, and sure enough, we've got a lot more root growth. So it actually matches up really well. And this was thrown together in, literally it took 5 minutes to scan and about 10 minutes to run. So it's reasonably fast. But what happens up here, this is the soil, and sure, in the PAM treatment, it looks like it's more aggregated. It looks like it's actually doing what the snot was meant to do. The snot is meant to bring it together into nice big chunks, and it looks like it's done that. And when we take a vertical slice through, again, it actually looks better. No real effect here. Nothing going on with the gypsum. And one of the things we can do is we can actually extract the pores. So we can look at the negative space. So we can see the roots and we can see the soil, but when we extract the negative space, we can actually see the pore distribution. And when we look at that, there's far fewer pores in the control than these. So in a sense, it's actually working quite okay. So that's where I've got to. I've done my wheat experiment and it didn't work. I will be playing with it again. I have to acknowledge CRDC, GRDC for the root stuff at the end, but definitely Beck and Kylie who did the work that this has been presented on. So I'm happy to take questions, but I think Neil's answered most of them anyway, John, so.